This is Chapter 4, Product and Service Design. So strategic product and service design, it's the essence of an organization, is the goods and services it offers. So every aspect of the organization is structured around them. So product, service design, or redesign should be closely tied to an organization's strategy. So what does product service design do? So the first thing it does is translate customer wants and needs into a product or service requirement. The second is refine existing products and services, develop a new product or service, you formulate quality goals, you formulate cost targets, you can construct and test prototypes, you document specifications, translate product and service specifications into process specifications. And it involves interfunctional collaboration. So here's some key questions. Is there a demand for it? Product size, demand profile, the market size and demand profile. The second question is, can we do it? The manufacturability of it, the capability of an organization to produce an item at an acceptable profit. And serviceability, the capability of an organization to provide a service at an acceptable cost or profit. And what level of quality is appropriate? Customer expectations, competitor quality, and does it fit within the current offering? And does it make sense from an economic standpoint? You take into account the liability issues, the ethical considerations, sustainability issues, costs, and profit. Does it make sense economically? So reasons to design or redesign. So the driving force for product or service design or redesign or market opportunities or threats. So there's economic, there's social and demographic, there's political, liability, legal, competitive, cost or availability, and technological. So here's where you get ideas for new products. So one option is from the supply chain. So you can go to your customers, your suppliers, your distributors, your employees, your maintenance and repair personnel, and look for, what are the problems, what are the solutions, what are some ideas to make this better, make it different. You can also do competitor-based ideas. This is study how the competitor operates its products and services, and many useful ideas can be generated. So the next is reverse engineering, dismantling and inspecting a competitor's product to discover product improvements. Then there's research-based ideas. So research and development, an organization, it's organized effort to increase scientific knowledge or product innovation. So there's three kinds of research. There's basic research. This is the objective of advancing the state of knowledge about a subject without any near-term expectation of commercial applications. The second is applied research, and this has the objective of achieving commercial applications. And then there's development. This converts the results of applied research into a useful commercial application. Legal considerations. So there's a couple of legal considerations. First is product liability. This is the responsibility a manufacturer has for injuries or damage caused by faulty product. And some of the commitment cost, litigation, legal and insurance cost, settlement cost, costly product recalls, reputation efforts. Informed commercial code, uniform commercial code. So this is the UCC. You see this on extension cords. It's a little stamp. It carries an implication of the merchantability and fitness of a product. So if it's UCC certified, you're not going to burn down your house, or lower likely you're going to burn down your house from this extension cord. Ethical considerations. Designers are often under pressure to speed up the design process and cut costs. So most recently, Volkswagen had a big blow up where they cut corners on the design by implementing some software that, while it was taking the emissions test, it would pass the emissions, but then when it wasn't taking the emissions test, the software was different so that the emissions would have failed, but it gets better performance. So that's an ethical example. There's pressure to force trade-off decisions. What if the product has a bug? You release the product and risk damage to your reputation. You work out the bugs and forego revenue. So Microsoft is famous for this. You get a new version of software and it's full of bugs. So they're first to market, but then they take some time working out the bugs. I had actually attended a presentation that had a tester from Microsoft give the presentation, and it's probably surprising to most of us that Microsoft actually knows what the bugs are when they release the software. They just don't tell you. They're constantly testing the software to determine what's broken and working on fixing it, but at some point they decide we're going to release it with these known problems, and then they plan on doing releases. Sustainability. So the question is, does this product harm the environment? Some of the key aspects of designing for sustainability is cradle-to-grave life cycle assessment, end-of-life programs. When this thing is over, when this product is over, what's the sustainability considerations? So then there's 3 hours of sustainability, reduction of cost of materials used, reusing parts for return products, and recycling. The inventor of the K-cups, his own issue, I understand that he his biggest regret in inventing the K-cups is the amount of those little cups that are going into the landfill. So, so he invented this really cool K-cup thing, but now there's millions and millions of these K-cups going into the landfill. So that's an example where the product is not necessarily that sustainable going into the landfill. So there's stages in a product or service life. So at the beginning, it's introduction, and then there's growth, and then maturity and decline. So this is demand. So at the beginning, it's slow, and then you have growth, and then as the product matures, it starts to taper off, and then you go into decline. Standardization. So standardization is the extent to which there's an absence of variety in a product, service, or process. So products are made in large quantities of identical items, and every customer or item process receives essentially the same service. So then there's mass customization. So mass customization is a strategy for basically having standardized goods or service, but incorporating some degree of customization in the final product or service. And so there's a couple of methods that you can use for this. One is delayed differentiation and modular design. So delayed differentiation is the process of producing but not quite completing a product or service until customer preferences are known. It's sort of a postponement tactic. So a piece of furniture, you produce it, but you don't stain it, and then the customer chooses a stain. Or you have all the pieces, and then you put the last little piece together. So like a computer, you have all the parts to a computer, and then you say, well, how much memory do you want? What size hard disk? And you put those pieces in at the last. Modular design. So this is a form of standardization which parts or groups or modules are easily replaced or interchanged. So you can easily diagnose failures. It's easier to repair. It simplifies manufacturing assembly. Training costs are relatively low. Disadvantages: a limited number of possible configurations and limited ability to repair a faulty module. So if I go back to a computer like a desktop computer is a good example of a modular design. There's a slot there for your hard drive, and you can put whatever size hard drive you in. You could add a hard drive. You can have different disk drives, like a CD drive, a DVD drive, a read-write drive, So those are examples of modular design. Reliability. So reliability is the ability of a product or service to perform its intended function. Failure is a situation in which the product does not perform as intended. And reliabilities are specified with respect to certain conditions, so normal operating conditions. We're actually going to go into reliability in more detail at the end of this chapter as a supplement, so we'll go into that a little bit more later on. Robust design. So robust design is where the products and services can function over a broad range of conditions. When things get really cold or really hot, they tend to fail. So a robust design might extend the operating range or vibration. Quality function deployment. This is a method. I'm just going to mention it just in case you ever run across this. It's a way to integrate the voice of the customer, and the purpose is to ensure customer requirements are factored into every aspect of the process. You listen to and understand the customer is a central feature. So what they have is something called a house of quality sequence. So you have customer requirements, and that goes into design characteristics, and then design characteristics go into specific components, and then specific components go into production processes go into a quality plan. Concurrent engineering brings engineering, design, and manufacturing personnel together early in the design phase. It may involve manufacturing, marketing, purchasing personnel in integrated cross-functional teams. The idea is you get the views of the suppliers and customers also. The purpose is to achieve product designs that reflect what the customer wants, as well as manufacturing capabilities. So it's bringing. It's real easy to make something you can't build or manufacture, or something you manufacture that the customer doesn't want. Concurrent engineering blends those together. Computer-aided design. This uses computer graphics to design. Some of the advantages is you can get designs 3 to 10 times faster and higher productivity. You can create a database for manufacturing information and product specifications, and the possibility of engineering and cost analysis on proposed design. There's something that includes finite element analysis. That's where you can actually put like gears together and see if you build these two gears, will it work? So it enables developers to perform simulations that aid in the design analysis and commercialization of new products. Then product requirements. So the designers must take into account production capabilities. So this is production requirements. Equipment, skills, types of materials, schedules, technologies, and special abilities. Manufacturability, this is the ease of fabrication or assembly. It's important. Implications for cost, productivity, and quality. Component commonality. So when products have a high degree of similarity, you could use that component for multiple products. So this is really modular design taken down to the component level. So you have savings on design time, standard training for assembly and installation, opportunities to buy in bulk from suppliers, commonality for parts repair, and fewer inventory items that must be handled. Service design. So this is where you actually take, you design your service. So a couple of issues in service design is degree of variation in service requirements and degree of customer contact and involvement. So here's some differences between service and product design. Products are generally tangible, services are intangible. Services are created and delivered at the same time. So services cannot be inventoried. Services are highly visible to customers. Some services have low barriers to entry and exit. Location is often important in service design, with convenience as a major factor. And service systems range from little or no customer contact to those with very high customer contact. And demand variability alternatively creates waiting lines or idle service resources. So if you have that demand going up and down, you're either going to have idle resources or waiting lines. Operation strategy. So it's effective product and service design can help the organization have a competitive advantage. Products and ancillary services to increase sales. You can use multiple use platforms, implement tactics that will get high volume while satisfying customer needs for variety. You need to continually monitor your products and services for small improvement opportunities, and reducing the time it takes to get a new product or a redesigned product or service to market can be a good operation strategy as well. So this is the supplement for Chapter 4, it's reliability. So we mentioned this already. The reliability is the ability of a product, part, or system to perform its intended function under prescribed set of conditions. So it's expressed as a probability. So the probability that a product or service will function when activated. And then the second is the probability that a product or service will function for a given length of time. So reliability is the probability. So finding the probability under the assumption that the system consists of a number of independent components. So you have independent components. So an independent event that doesn't interfere with another independent event. We'll go through this and maybe it'll become more clear as we go through it. So rule 1, When two or more events are independent and success is defined as the probability that all events occur, then the probability of success to the product is equal to the product of the probabilities of the events. So here you have button A, button 1, and button 2. So in order for this machine to work, you have to press button 1 and you have to press button 2. And so now if the probability of button 1 working is 95% and the probability of button 2 working is 88%, then the probability that the machine will work is the product of those two, or 83.6%. So then, even though the individual components could have high reliability, the system reliability could be completely lower. So one way to increase reliability is redundancy. So this is the use of backup components to increase reliability. So rule 2, if two events are independent and success is defined as the probability that at least one of the events will occur, the probability of success is the probability of either one plus 1 minus the probability multiplied by the other probability. So we'll show what this is. So here you have generator and the power company. So the probability that the power company will work is 97%, and the probability that generator will work if the power is out is 90%. So to calculate this, you go 1 minus 0.97% times 0.9%, and you add that to the 97%. So this 97%, it's going to work 97% of the time, and then you add to it. So during the 3% that it's down, you multiply it by 0.9, and so then your probability goes from 0.97% to 0.997%. So your probability increased. Okay, and then rule 3 is when two or more events are involved, the success is defined as probability at least one of them occurs. The probability of success is 1 minus P of all fails. So here, here's the probability. So a student takes 3 calculators to her exam. Only one needs to function for her to be able to finish the exam. What is the probability that she will have a functioning calculator to use while taking the exam? So here you have the primary calculator, 85%, the second calculator, 80%, and the third calculator, 75%. You just say, what's the probability that all 3 will fail? And that's that 1 minus 0.85 times 1 minus 0.8 and 1 minus 0.75, and you get that 0.9925. So she has a 99.25% chance that her calculator will work by having 3 of these calculators. So what is the system's reliability? So here's an example where you got 3 independent events with redundancy on each one. So we go through each one, you do them independently. So you start out with 0.8 and 0.95, you calculate that probability as 0.99, and then you get this 0.75, 0.8, 0.85, and that comes out to be 0.9925, and then the other 2 comes out to be 0.97, and then you combine those together and you get a probability of 0.9531. So there's something called the bathtub curve. So when you first produce an item, there's something called infant mortality, and this is the first few items, you just have a higher failure rate, and then you go for a long time with very few failures, and then the system starts to wear out at the end, where you have a lot of failures. So So what you do in a factory is a lot of times you want to just run the system for a little while, um, and just to weed out the infant mortality. So let's say you sell light bulbs, you might turn on the light bulb for an hour and then turn it off, and that'll weed out the infant mortality. Um, and then uh, and then as far as warranties, so there's a couple of strategies with warranties. So there's the early warranty, sort of the free warranty you want that covers that infant mortality. So that one customer that gets that one thing that has that infant mortality, they're covered. Um, and then another strategy is sort of this extended warranty that just goes through both the infant mortality and the few random failures. And then so that way you're covering that period when there's very few failures. That's the warranty. As far as the wear out period, most companies don't want to sell you a warranty for that failures due to wear out. Those are very expensive warranties if you buy those. Distribution and length of phase. So you want to really identify the distribution and length of the failures. So there's something called mean time between failures. Infant mortality can be modeled using a negative exponential distribution. So that left side of the bathtub curve, here's here's what it shows. That sort of this exponential distribution. And there's something called availability. So availability is the fraction of time a piece of equipment is expected to be available for operation. So it's mean time between failure divided by mean time between failure plus mean time to repair. So let's say that I have a car that it breaks every month, and it takes a week to fix it. So now my mean time between failure is a month. My mean time between failure plus mean time to repair, which is a week. So it's 4 weeks divided by 5 weeks. So my availability is 80%. So 4 divided by 5. Here's an example. A student, a John Q student, uses a laptop. The laptop operates 30 weeks on average between failures. It takes a week and a half on average to put his laptop back into service. What is the laptop's availability? MTBF divided by MTBF plus MTR. So 30 divided by 30 plus 1.5 is 95.24%. Okay, so this has been a summary of Chapter 4, Product or Service Design. You have sources of ideas, legal and ethical considerations, sustainability, product or service life stages, design approaches and tools, and then the differences between service and product design. And then under reliability, we talked about reliability rules, the bathtub curve, and availability.